of our workshop. Now we will listen a tutorial by Vladimir Stanovov. The title, Modern Differential Evolution, from Simple Adaptive Schemes to Hyper-heuristics. You are welcome.
Okay, thank you. Please let me know if you can see the slides.
Yes, we can see slides.
Okay.
Perfect.
Great. So let us begin. We will talk about differential evolution today. So yesterday there were several mentions of this algorithm, but this is a tutorial, so we will try to keep things easier, at least in the beginning, and then maybe we will try to see some more complicated things. Okay, so first of all, I should say that this tutorial is a follow-up to a keynote a lecture that I gave 3 years ago on this conference about trends and challenges in differential evolution. But there are some new things that I would like to discuss. Okay, first of all, what are we talking about? We are talking about numerical optimization. So we have a function, we have numerical x1, x2, x3, x something. We have f of x, and we should find the minimum. So what is the problem? Yeah, the problem is that we have black box. We don't know what kind of function do we have. So we may try to guess, but maybe we will be not successful. So we should solve it as black box. We know nothing about the function. So which algorithm should we use for that? If we look at one of the latest competitions on numerical optimization, this is from the Congress on Evolutionary Computation 2022, there were 13 algorithms for numerical optimization. So what are these? Well, actually, if you look closer, 10 out of 13 are variants of differential evolution, even if it doesn't say DE in the name of the paper. If you look closer, you will see that this is actually one of the types of differential evolution. So why? There are many modern real parameter optimization algorithms like covariance matrix adaptation, particle swarm optimization, and some other methods like fish school search or wolf pack search. Why differential evolution is dominating all of these other methods? Well, let us try to understand this. So actually, what are the questions that we should ask? What makes it so special? And well, probably it's the difference-based mutation, as you can think from the name. How does it work? And maybe there are some other components of success of differential evolution, and so on. So what are the parameters? How do they influence performance? And how do we balance exploration and exploitation? And so on. So let's start with the basics. Now that I asked some difficult questions, let's start from the beginning. So how does it work? Well, first of all, we have random initialization. Then we have this key part of difference-based mutation. Then crossover selection, which is actually replacement, but the terminology is selection, and then we go back. So, for example, the random initialization is very simple. So we just make maybe 100 random points in the search range, and that's it. So nothing really to talk here about. So next, this is the key part, difference-based mutation. So we take one vector randomly and add scale difference of two other randomly chosen vectors. And that's it. So yeah, we have a parameter here. It's the scaling factor f. So we will talk about it a little bit later. So let's first look into how can we draw this thing. So we have some vector xr1, xr2, xr3, several vectors. So we calculate the difference vector xr2 minus xr3, and then scale this difference, and we get and add this to one of the other vectors, and with this operation we get a newly created mutant or donor vector. Next part is crossover. So we just take our new vector and combine some parts of it with current individual xi. So also really simple scheme. In the picture you can see how it works. So in the top right corner is the current point xi, and the left bottom point it's mutant vector vi. So, and with crossover, you can get one of three points that are shown with squares. So this is crossover. Next, we also usually use some kind of boundary condition checking, because we do not wish to search outside of our boundaries, but this is not really important. And the last step is selection. So if our new individual is better than the old one, we just replace it. So very, very easy. Of course, there are more complicated mutation strategies, because, as I said, this is the key part of any differential evolution. So you just take maybe two scale differences, or maybe scale differences between current and randomly chosen individual, or current or best individual, and so on. So the last one, current to be best, is considered to be one of the most efficient schemes, and in modern differential evolution, you actually see only this mutation strategy. Okay, so how do we implement differential evolution? It's not that difficult, actually. So this is the code. This is all you need to do in Python. Of course, maybe in C++ it will be more lines of code, but I just wanted to show you how simple it is. So you see, we have parameters. We have some function, which is just x squared. Then we initialize population, calculate fitness. We just create a vector for the new individual. Then we have two loops for generations and individuals. We take three random indexes. We make difference-based mutation, or otherwise we take component with crossover probability CR. Then we evaluate the solution. If it is better, we replace it. That's it. You don't need anything else. It is very simple, and well, that's one of the reasons why it is so popular. So, for example, I mean, the CMA-ES algorithm is also highly efficient, but it's not very popular because it requires some matrix multiplication and stuff like this. So, well, this is much simpler. Okay. Now let us try to understand how it actually works. So we will try to visualize what are the points that differential evolution creates with this different base mutation. And we will use different scaling factor values, so different f values. We will build some 2D histograms. So let me show you. So this is the example. We have 8 random points, and our scaling factor is 0. So we do not move the points. So we have a heat map on the right where we just have the same points. So nothing interesting here. But if we set f to 0.1, this is what we get. We have like a little cloud around each point. And if you look closely, the shape of this cloud actually copies the shape of the positions of the original points. I mean, in some sense, but every point has a different cloud around it. And for example, the 2 points on the top right, which are close to each other, you can see that their clouds are combined. Okay, but this is 0.1. It actually looks like local search. If we increase to 0.3, okay, well, this looks just like some random search. Why would this work? Some person would maybe would ask. If we increase f to 0.7, we get more like random distribution of points, but we don't really see any particular patterns here. But what if we not just set f to a fixed value, but generate it randomly? So from 0 to 1, for example. Now this gets more interesting because from each point we have this kind of rays that go in different directions. So these are the directions in which we perform the search from each point. And if we set, for example, a different distribution, like a normal distribution with a mean of 0.5 and some variance of 0.2, we see that in this case, we do not search really close to the point, but we distribute our search further from each point into the search space. Okay, so here are some GIFs, some animations of how this actually works. So on the right, you can see the positions of points that differential evolution would probably look into. So these are not all the points that it checked, but some kind of histogram or two-dimensional probability distribution of generated points. And here you can see on the restricting function some interesting pattern. At the end of the search, you see that actually you can see these cells, this local minima that you can observe on the function below. So actually, the differential evolution, thanks to this difference-based mutation, it is capable to capture the structure of the problem, and with this, it actually allows to jump from one local optima to another, and this really helps in high-dimensional problems. Another example is a classical Rosenberg function. So you can see here that at the beginning, it's more like random search, really, like we saw in previous pictures. But then at the generation around 15 or 20, we can see that it captures the structure of the landscape of the function, and then just goes down this valley and finds the optimum. So it just converts to a single point. So this is how the magic in differential evolution happens. So the key thing to understand here is that the distribution of generated points depends on how the population is located at each time step. So the population actually distributes in the search space in the way that mimics the landscape of the problem. So this is the main idea. Okay, so right, we can make some visualizations, but we actually want it to work really well. And I said it works very well and so on, but well, it's not that good. And I mean that there are some significant problems, and these problems are with parameter adaptation. So as I said, we have two main parameters, scaling factor f and crossover rate CR, and also third parameter population size, but it's not that important. So over the years, there were many attempts to propose some tuning of these parameters. So until now, the shade algorithm is considered like one of the most efficient parameter adaptation schemes. So let's look into this shade. So this is a catchy name, which stands for success history based adaptation. So the idea is we generate scaling factors and crossover rates randomly. Then we have several memory cells. We store successful values there. And if our solutions are improved with some values of F and CR, we store these values. And then we calculate weighted mean. And the weights are the improvement values. And then we update the memory cells. Okay, I know this sounds complicated, and well, probably it is, but later I will show you a simpler method. So this is what happens to F and CR during optimization of different functions. So as you can see, these values, they actually change a lot during the search process. This is all if you can say, this self-adaptation. So it's all based on which values perform better at each time step. So there are other features in the shade algorithm. So for example, it has an external archive, like we store some of the good solutions to an external set, and then we use it in the notation. But more important is the L-shade algorithm, which is from 2014, 10 years ago it was proposed. And the key idea is that we add to shade, which is actually already very good, we add the linear population size reduction, LPSR. So we just set a huge initial population and then decrease its size. So the idea is that at the beginning we spread the points in the search space, and then we just remove bad points, and at the end we have like 4 points. But at the end we converge much better, much faster. So how can we understand which parameter values are good or bad, or how do we tune them? Well, several years ago, I had this idea of expected fitness improvement, or EFI. So the idea is the following, similar to the pictures that I have shown you before. So we just create a grid of F values, and at every generation, we sample a lot of solution and just see which F values give us improvements. So this is the key concept. We can use it for F, we can use it for CR, for other parameters if we have them, and then we can build some heat map profiles. So these are some parameters for the experiment that I will show you. And it looks something like this. So this is a very simple function, as you can see on the right, like a bent cigar is a single local optimal, but it's ill-conditioned. And the upper graph shows us that the best F is actually, well, something close to 0. And as I showed before, this is actually local search. But is it really a good idea to set F to very small value? Well, in fact, it is not. In fact, it is better to set F to something like 0.4 or 0.5. And the black lines here on the graph show that this is actually what the success history adaptation did. But why is this difference? Well, the reason is that the expected fitness improvement shows you immediate improvement. So you can improve your solution with just very small F value. But then in the long term, maybe in 10 generations, you will not go very far from current position. You will not be able to find global optimum. The bottom graph, by the way, shows the distance histogram in the population. So you can see in the beginning, the distance is high, then it decreases and stays close to 0 until the end of the search. So what about other functions? Well, there are some interesting things to discuss here. So for example, this is a beta-strigging function. So it's kind of deceptive because it has a a false local optima in the center and a global optima on the top left. So we all again see that actually the best value of f is 0, but this is not true. We know that we should set some other values. And if you look closely, you can see that there are also lines at f equals 1 or minus 1. So why is this? Well, if we remember how differential evolution performed on restricting function in the animation that I've shown, it is able to jump from one local optima to another. And for this, because the distance between optima is the same, you need f equal to probably 1 or maybe 0.5. You can also see lines at 0.5. And that's why this happens. On the lower graph, by the way, you can see that the distance histogram splits into several parts. So there are some subgroups of points in different parts of the search space. Okay, some other examples with JDE with different parameter adaptations. So you can see that the picture is significantly different. So actually these pictures depend on the adaptation scheme. Previous were with shade. But still there are some curious things, like here in this hybrid function, we can see horizontal line at 0.5, at 1, minus 1, sometimes 0.33, and so on. So this function again has multiple local optima, which have the same distance between them. Some other interesting examples is, for example, if we use shade, but with current to best. So previous examples were with round 1, the simplest strategy. If we use current to best with shade, well, the picture is quite different. So the best improvements are at around 0.3, 0.4. But again, we set a little bit bigger values because we want to go further to get to global optima faster, probably. Also, you can see these horizontal lines at 0.5 and 1 in case of shade. Maybe some other interesting cases here. Okay, maybe I will skip a couple of these slides and show you this one, because this one is really interesting. So this is the case of JDE algorithm. And well, usually we set f as a positive value, like from 0 to 1. Why? Because in current to best, we go towards one of the best solutions. And well, if we go there, well, it's probably good if we go towards better solution. But it's not always the case. For example, here we see that like from generation 150 to 300 something, we actually need to go backwards from the best solution, and this gives us improvements. So we see these yellow dots below the graph, like at -1, -2, and this gives us improvement. But we usually don't do this. But sometimes it could be beneficial to go backwards. Okay, so as we can see that the EFI allows us to look into how the adaptation of F occurs, and we can spot some trends here, like 0.5, 0.25, 0.75, and so on. We can do the same for crossover rate. Let us see. So this is the graph for crossover rate. It is not so obvious, actually, what happens here. But actually, this says, okay, let's set CR to 1, and we will be in a good spot. But it's not always the case. For example, for this Schwefel function, better CR are close to 0 at the beginning and close to 1 at the end of the search. Also, on the bottom graph, you can see how the distances are distributed. So we have points located in different local optima. I will remind you that this is a 10-dimensional case, so it's not 2-dimensional like on the picture on the right. But there are some interesting cases here, like here you can see this switching behavior between large CR working great and small CR working great, and then again large CR, small CR, and so on. For example, here you can see it clearly. So first 100 generation, you should set CR to 1, then you should set CR to 0, then maybe again to 1. And this is what we observed in many cases, like in different functions. So based on these findings, actually, there was a small idea. What if we just set CR to 0 or 1? So either we take all values from the mutant vector or almost all except 1 values from the current vector. And actually, it worked quite well. It improved the performance, especially in 20-dimensional case, based on this, just looking into pictures of how the algorithm works. Okay, so as I said, this EFI could be helpful to analyze what are the parameters that your algorithm actually wants to have. And you can apply this to anything, any other algorithm, maybe genetic algorithm, particle swarm optimization, or anything else. Okay, let's go on. As I said, the development of differential evolution, the modern age, if I can say so, started with shade algorithm, but then a lot of other algorithms were designed based on shade. For example, this is from 2017, the JSO algorithm, and as you can see, there are a lot of ifs in this algorithm. So if this, then do this. Like this is a joke about artificial intelligence, which is just if, then else, and so on. But it works very well. Then in 2019, we had an idea. What if we add selective pressure to differential evolution? As I said in the beginning, there is selection in differential evolution, but it's not like classical selection in genetic algorithm, like tournament-based, proportional, and so on. So the idea was to add this selective pressure. For example, rank-based, like rank selection in genetic algorithm. We can use tournament selection, exponential rank selection, linear rank selection, proportional, and so on. So these are graphs of different selective pressure. So this gave the L-shade RSP algorithm, which is actually my most cited paper, and it has a terrible mistake in it. You can have a look, but I will show you at the end. So this is actually JSO with selective pressure, and it took second place in 2018 at the Congress on Evolution and Compilation competition. Next was the NL-shade RSP algorithm in 2021, which is a further modification, and the modification is this one. As you can see, it's very simple. We use not linear population size reduction, but non-linear. And it actually gave a little bit of boost of performance for the algorithm. There were some other tunings like adaptive archive usement, using so probabilities to use archive or not to use archive, and so on. But this is not very interesting in the moment. So just a few results that I would like to show you for the NL-shade RSP algorithm. So for example, here you can see some of the best methods of CEC 2020, the IMODE and AGSK algorithm, as well as J2020, which is JDE with some tuning. And the pluses are where NL-shade RSP was better, and minuses are where it was worse. And you can see most are pluses, except for maybe some cases for IMODE. This is a 10-dimensional case, 20-dimensional case, it is mostly better here. Also some Friedman ranking of the same algorithm, and you can see in the 10-dimensional case the MOD is better, but in 20-dimensional case it is not. And the final ranking of 2021 was that the NO shader SP had the first place. This was the first victory of this algorithm. Okay, at this point I would like to make a little detour and discuss about some other algorithms. So as I mentioned, there was this IMODE algorithm, and well, it worked very well. But actually, when I looked into the code of this algorithm, I found this weighted to phi best mutation strategy. And it looked very strange to me. Why? Well, because it is center-based. So it generates vector from the center of the search space. And if we shift the function, so shifting is this one. This is very simple picture, I know, but if we just shift the function, we still generate vectors from the origin of the search space. So, for example, if we take our function and shift them to maybe 10,000 to the right, all of them, all variables, you see the performance of NO shader SP doesn't change at all, but the IMODE becomes much worse. So it depends on where the function is located in the search space. This is a really bad thing to have for an optimization algorithm. And well, it was accepted and was improved, several publications, and well, I was quite confused. How did this work? There are other cases where some authors try to create new algorithms which are not differential evolution, but in fact, if you look closely, like this AGSK, Adaptive Gaining Sharing Knowledge algorithm, has some ideas about juniors and seniors exchanging knowledge, but in fact, it is the same current to best mutation strategy. It even has the same population size control. So it is just a variant of L-shape. And well, to my opinion, this is not very good science. Okay, speaking of bad science in meta-heuristics, you can look up this paper here about meta-heuristics and how new ones are proposed, which are actually not new ones, but just new names for the same stuff. And I hope this will not happen to differential evolution, but probably it already is. Okay, let's go back. Sorry. So as you can see, there is a little bit of crisis in differential evolution because for 10 years, no one has proposed anything better than L-shape, at least maybe for 8 or 9 years or something. So, okay, maybe people are not very good at designing new algorithms. And well, I certainly know that my ideas are mostly bad for the performance. So then the idea is the following. Let us try to use some hyper-heuristic approach. That is, we will try to automatically design new types of differential evolution or maybe some search operation or parameter adaptation techniques, and maybe we will see something interesting here. So the first idea was to use genetic programming for this purpose. So we just use this tree-based genetic programming. Then we run the differential evolution, and each evaluation in genetic programming is actually testing the whole differential evolution algorithm. So, for example, this was a set of functions that I used, the experiments, inputs, outputs. And please have a look at the inputs. There is this success ratio. When I put this here, I didn't think about it, but I just thought, okay, let's add this. And the designed heuristics for parameter adaptation actually performed sometimes better than the NO shader SP algorithm. Okay, this is interesting. How do these heuristics work? Well, something like this. I know this doesn't tell a lot, but at the beginning of the search, you should set CR to big value, and it also depends on success rate somehow. But in practice, it looks like this. So yes, this is different from the shade parameter adaptation. It works in some strange way, but if it works, it works. Who cares? Yes, so same we can see for crossover rate adaptation. And actually, if we compare it to some other algorithms from CC 2021, it performs not so bad. So this was like a proof of concept. We can create new heuristics for parameter adaptation automatically, and it may perform well. So the next step was this, the LNPADE algorithm. So I was quite lucky to get an interesting paper for review for the CC 2022, which discussed like an unlimited differential evolution. So it was a variant of differential evolution that saved all solutions from all the search process. And from this, this was the idea to use two populations of best and latest solution. And actually, the general scheme is, oh, sorry, some pictures are, some text is moved. Okay, I will just switch to plan B here. Okay. Sorry. Okay, it's still broken. Sorry. Okay. So let's just go on. From this, the LSRT-DE algorithm was developed. And actually, I found that there are some forgotten ideas in differential evolution, like crossover rate repair, which is a very good thing and works very well, and also added to LSRT-DE. But the main thing is this one. And you may ask, what is this? Yes, so on the x-axis we have SR, success rate, and y-axis we have F values and p-best values. Where did this come from? Well, I did not think it with propose it just from my head, because the approach for this was again genetic programming. So I tried to design new parameter adaptation techniques, especially for LNPADE with genetic programming. And this is what it gave as a result. Can you see it? Probably not. I didn't see it for 1 year. I looked into these pictures for 1 year, and then I looked into these particular pictures, and I saw, okay, well, this looks like a square root of success rate. Okay, let's maybe explore this idea. What if we set F values not with success history, but just we use success rate, like the number of improved solution divided by population size. We put it to power 1 divided by C, where C is a constant, and use this value for parameter adaptation. Of course, we can change C, not just square root, but cubic root, fourth order root, and so on. The fourth order root actually turned out to be the best variant. And you can see the comparison. We have success history adaptation. As I said before, it is quite difficult, and success rate based adaptation, much simpler. And I would never think about it if not the genetic programming that would suggest this idea to me. Okay, but can we do even better than this? Yes, we can. We use again the hyper-heuristic approach, and we design parameter adaptation technique more precisely. But now we know that we need success rate to control scaling factor. So we can also use normal, students, or Cauchy distribution for this, and these are the results. So actually, these graphs with cubic root, fourth order root, they were close to truth, but actually F should start from 0.4, go to 0.665 or something, and this is all you need to do. And the interesting part here is that actually at the very beginning, when differential evolution was proposed, some theoretical studies have shown that you don't need F lower than 0.4. This is bad for research process. And you do not need F more than 0.7 or 8. And this is exactly what we got with hyper-heuristic approach. So we tried to tune the parameter adaptation technique, and it resulted in what the theory has predicted like 20 years ago. So the same can be applied to any other parameter, like p% best. You can see the graph on the right, and actually it shows that if success rate is small, we should make a broader search. And if the success rate is high, we should concentrate on the best solution and just go towards our optimum. Okay, so now you know where this picture came from, and this is the part of LSRTD algorithm. So as I said, if the success rate is small, we should maybe go around, look around, and if it is large, we should go to one of the best solutions. So here are the parameters, and the important part here is I showed some different benchmarks before CC 2017, 2021, 2022, but LSRTD is good for all benchmarks with the same parameter. So even the population size is fixed. So here are the 3 competitions, and on this slide you can see the comparison with the top methods from different years, also like L-shader SP and L-shader SP, and this is just a little bit easier to understand because it's Friedman ranking, and the best results are with LSRTD. It is much better than other algorithm except for 10-dimensional case. And same is true for CC 2022. Yes, here the other method is a little bit better. The AA for egg and 100 is better, but if we change a little bit the population size in LSRTD, it will be better. And finally, CC 2024, this year's competition. I first compared it to the algorithm that already existed before the competition. But after the competition, well, here it is on the first place. I was very lucky with this result, but it's not perfect because for constraint optimization, it took the second place. Okay, but still not so bad. Okay, let me change back to these slides because I added some more. So in conclusion, what I would like to say, first of all, try to visualize the heuristics that you are trying to develop, because it will give you intuition and understanding of how it works, how your genetic algorithms or particle swirl optimization or differential evolution, genetic programming, just try to make some pictures. The more pictures of different types you make, the better it is. So the key concept of differential evolution is that it is a directed population-dependent search. And for example, you can see this with expected fitness improvement. So in the recipe for parameter adaptation technique is, well, you should not maybe follow the immediate rewards, but look into the future, what will be good for the search in several generations. And also several things that I would like to say that, well, yes, you can create new parameter adaptation techniques, but it is a computationally hard problem. But it allows you to find new solutions that nobody has ever thought about. So this idea with success rate based adaptation, it is very simple, but no one tried this. And I would not try this if not for genetic programming. So this is kind of thinking out of the box that hyper-heuristics allow you to do. So what's next for differential evolution, and what can you do to improve it? Well, there is still a lot of things to learn, and maybe automatic design of algorithms is one of the key concepts that could probably give us new ideas of what to do. And you can, of course, apply it not to differential evolution, but to other methods. But maybe we can find some similar operations to difference-based mutation, but this is yet to be discovered. Okay, some final remarks that you can have a look at my GitHub. You can see that the most popular repository is L-shade RSP. And also the latest LSRTDE is also there. You can download the code, check it, use it, whatever you like. Also, I recommend you to visit the repositories of this guy, who is the main organizer of all competitions, and you can find a lot of codes of the best methods from the last maybe 20 years. The best optimizers are located here. You can find them all here. And as a bonus, well, this was more like a fun thing to do. As I showed you this expected fitness improvement pictures, actually you can turn them into sound. Like you can consider them as a spectrogram and transform spectrogram into sound wave, and you can listen to how differential evolution performs its search. So feel free to use the QR code and listen to differential evolution, but I warn you, this is not this doesn't sound very nice. Okay, thank you for your attention, and I will be glad to answer your questions.
Thank you very much for your presentation. Dear colleagues, you have possibility to ask a couple of questions. Professor Yeremeyev, you are welcome.
Thank you. Can you hear me?
Yes.
Yep.
My question is about the nature of mutation operator in differential evolution. It seems that the result of mutation here always belongs to a linear subspace defined by the current population. And if it is correct, then the whole population may be trapped in such a subspace, which is far from the global optimum. Do you agree with this, or maybe you have observed such problems with differential evolution and how to overcome them?
Okay, I see. So yes, this might happen, especially because, well, actually our scaling factor f is usually below 1. It's from 0 to 1. So it's like it's always reducing the population, bringing it closer to each other. Yes. So, and if the population is located in some area and the global optimum is far away, so, well, yes, we will not get there. We cannot jump really far away with differential evolution. Yeah, this is a drawback. But, well, how can we fight this? We just generate points in the whole search space.
I'm sorry, my question is not about the distances, but about the linear subspaces. Even if you set f greater than 1, you would not be able to leave the current linear subspace, which is embedding your population. The current population may be embedded into some linear subspace of the search space.
Yeah, you're referring to this picture probably, yeah?
No, you would not be able to see this effect. But you see, if the whole population belongs to the x1 axis, for example, it lies on x1. x2 equals to 0 for the whole population, and x3 equals to 0. Then you apply your operators of mutation. You will always have zeros in x2 and x3. Is it correct?
Yes, yes.
So this would be a big problem if the optimum lies somewhere, for example, in the point 1, 1, 1.
Yes, I agree. I agree. This is absolutely true. So we only look in certain directions. But how can we probably not cancel this problem, but maybe make it smaller? We have quite big population, and we have two differences together in every mutation. So we go towards one of the best points, and also we go in some other direction at the same time. So this helps maybe to make this problem smaller. And the bigger population you have, the more variants directions to go you have. So actually, for example, in this picture, if you set not like 8 points, but 80 points, it's more like a uniform distribution in all directions. Of course, if the problem dimension is like 1,000 variables, well, you'll need maybe 1 million points to be able to do this. Yeah. So of course it has limitations, but yeah, you're right.
Okay, I see. You understand this problem, but there's no simple way out of it, right?
Yeah, well, probably not. At least
There
not
is
in
no
a black
necessity.
box scenario. Mhm.
There is no necessity because it's the best vault algorithm for now.
For these benchmark problems, if we have
Yeah.
different benchmark problems, no.
For any evolutionary algorithm, we can find enough functions which it will not be able to solve. So,
Yeah.
actually. Okay, ladies and gentlemen, it's we are over time. That is why any other questions you may ask in person.